Okay, so we're going to look at 2.6 in the notes, related rates. So basically we're doing story problems that are talking about taking the derivative and stuff. So basically 2.6 is just story problems that deal with derivatives and taking the derivatives of things. So we're going to use the properties that we talked about last week to actually take the derivatives. But first we're going to have to set up the formula and set up the picture maybe and kind of go through the steps. Now these will be tricky, so my plan is for you to get the notes today, Monday. Tuesday I will go over some questions on the homework and kind of give you some time to work on the homework, maybe look at some examples, and then Wednesday we're going to do an activity over related rates and Tootsie Pops. So we're going to kind of spend a couple days going over these because I think these can be tricky. So as I look at example one isn't necessarily a story problem, but it's going to kind of use related rates. So as I look at example one, I want to assume that x and y are both differentiable functions of t. Don't worry about that. All it's saying is that I can take the derivative of x and y. Find the required values of dy over dt and dx over dt. So I give you the function x squared plus y squared equals 25. That would be a circle. Not really important, but just so you know. So I want to know dy dt. I tell you I want to know dy dt when x is 3, y is 4, and dx over dt is 8. So since they give you dy over dt and dx over dt, we're going to, whenever I take the derivative of x and y, we're going to throw those out at the end. So let's go ahead. I have my x squared plus y squared equals 25. Let's go ahead and take the derivative. Power rule, that'll be 2x dx dt. Since they give me dx dt, dy dt, like I said, whenever I take the derivative of x or y, I'm going to put dx dt after it. Plus 2y dy dt equals 0. So kind of like implicit, but we're not really putting y prime, we're putting dx and dy both. Now I want to know dy dt when x is 3, y is 4, and dx dt is 8. All you do is plug it in. So 2 times x is 3, dx dt is 8, plus 2 times y is 4, and I want to find dy dt. And then you just solve this for dy dt. So this would be 2 times 3, 6 times 8 is 48, plus 8 dy dt. So 8 dy dt equals negative 48. Divide by 8, dy dt is negative 6. So that's all for that one. So not too complicated, not really a story problem yet, just taking the derivative, plugging stuff in. If I look at B real quick, same sort of idea, except now I want to know dx dt. So if I take the derivative again, it's going to be 2x dx over dt plus 2y dy over dt equals 0. Let's go and plug in what they give me. X is 4, so I plug in a 4. I want to know dx dt, so that's what I'm going to be solving for. 2 times y is 3, dy dt is negative 2. So 8 dx dt minus 2 times 3, 6, 12 equals 0. Keep solving for dx dt, add 12 to both sides. 8 dx dt equals 12. Divide by 8. So dx dt equals 3 halves. So not too complicated, just taking the derivative like we did last week and then plugging in the information they give you. Okay, now everything that's kind of following part of the principle for related rates. You have to always take the derivative first, then you can plug in your constants. So just like we did here, we took the derivative first and then plugged in your constants. You have to take the derivative first when you do related rates before you start plugging stuff in. Okay, let's go ahead and flip to the next page. Let's actually look at a couple of these. So the nice thing about the video, since I'm not here today, is that you can actually get on and pause it if you need to stop and write stuff down. So here are some guidelines for solving a related rates problem. First thing you want to do is you want to identify the given. So we're going to talk through a couple of these. You want to identify the given. The unknown. And possibly draw a picture, depending on what the problem looks like. Second step is you want to write an equation. This is a big one. Write an equation relating the given and unknown. So we're going to write an equation relating the given and unknown. And we'll talk more about these as we actually go through some. So just write them down for now. We'll worry about understanding it in a second. The third thing is we're going to differentiate. And the fourth thing is substitute in. And what they give you, the known, the given, and solve for what they're asking for. So I know these can be complicated, I get it, but if you go through these steps, it should help a little bit as you kind of try to understand exactly how to do these. So kind of go through these steps in your head. Don't get frustrated because you're not sure how to get started, because they give you lots of information. Kind of go through it and identify the given, the unknown, draw a picture possibly, write an equation that's comparing them, differentiate, plug in. Okay, let's look at example 2 right above it. The radius r of a circle is increasing at a rate of 4 centimeters per minute. Find the rates of change of the area when the radius is 8 centimeters and the radius is 32 centimeters. A couple of things to know. As you're reading through this, whenever it is giving you a rate is always a derivative. Okay, kind of like we talked about earlier. A rate is the slope, a derivative is a slope, and slope is the rate that my y increases compared to my x increases or decreases. So whenever I talk about a derivative is always a rate. So as you read through your problem, anytime they give you a rate, easiest rate to kind of think of would be miles per hour, speed. Speed will always be a rate. Okay, centimeters per minute in this case. Something per something is always a rate, and in our case is always a derivative. So first thing I want to look at is I want to know what is the given, what are they asking for, and then maybe draw a picture if I need to. So the first thing I want to look for is I want to look at what they give me. The radius r of a circle is increasing at a rate of 4 centimeters per minute. So that's going to be dr over dt. Remember, my rate is always the derivative. So since it's increasing at a rate, that is my derivative. The radius is increasing with respect to a minute. Centimeters per minute. So dr, the change in the radius over the change in time. And that is 4. It's increasing, so that is a positive 4. Okay. Now, it is increasing at a rate per minute. So we don't really have to put anything with it because we'll kind of deal with that in a second, but it's per minute. Let's look at what they're asking for as I go through it. Find the rates of the change of the area. So I want to look at the change, the rate of the area. So that is the derivative, dA over dt, because it is the change of the area with respect to time. So dA over dt, that is what I'm looking for. And you could draw a picture if you want to. I'm not going to necessarily. I don't think it's necessary on this one, but you may want to draw a picture if it doesn't make sense, if things don't make sense to you. The second step is to write an equation relating the given and the unknown. I'm given the change in the rate. I'm given the change in the area. So as I'm looking at this, I am looking at the area and radius of a circle. So I need a formula that relates the area and radius of a circle, which is area equals pi r squared. So the second part, you kind of have to think about it. Look at your unknown, look at your given. They give me the radius, I want to know the area. Compare that is a circle. So that's going to be area equals pi r squared. Okay, third step is to differentiate. So if I take the derivative of this, this will be dA over dt equals the pi is just a constant, so bring the 2 out front, 2 pi r. I'm going to put dr dt, just like the first example we did. So take the derivative, do not plug stuff in until after the derivative. Take the derivative first. Now, as I look at it, I want to know dA dt, which is already solved for. So the fourth step is to go through and plug stuff in. So I'm looking for dA over dt, the rate of the area, 2 pi. Now my radius, they tell me, I want to know the change of the area when the radius is 8 and when the radius is 32. So I'm going to take 8, plug it in. And then dr dt, they tell me, is 4. So let's go ahead and do that. So 2 times 8 times 4, 64 pi. Now make sure, I'm going to be kind of picky about the labeling. This is the rate of change of the area over the rate of change of time. So this is going to be the area over time. So centimeters squared, because it's area and we're in centimeters, over my time is per minute. So over minute. So that is how the area is changing when the radius is 8. Now let's look how the area is changing when my radius is 32. So go ahead and plug it in. Instead of 8, plug in 32. Now let's think about this. If it says the radius of a circle is increasing, so if the radius is increasing over time, when the radius is 32 centimeters, let's think about this. What's the changing rate of the area? 32, the radius is bigger than 8, so we're expecting my area to be bigger. If the radius is bigger in a circle, the area is going to be bigger as well. So as I go through and multiply that, we are going to get 256 pi, make sure you label it, centimeters squared per minute. Okay? So make sure you label it, make sure you identify your given, your unknown, come up with the formula that relates them. I think these are doable. I get these are tricky and there's lots of information to keep track of. Go through those 4 steps. I think that'll be very, very helpful. Okay, let's go ahead and look at example 3. A spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instant the radius is A, 30 centimeters, and B, 60 centimeters? So first thing I look at this, and as I read it, I want to know how fast the radius of the balloon increasing at the instant the radius is da-da-da-da-da. So since I want to know the rate, I want to know how fast something is increasing, we are looking for a related rate, how something is increasing or decreasing. First step, let's look at the information they give me and what they want to know. A spherical balloon is inflated with gas at a rate, right there, rate. So anytime they tell me a rate, that is a derivative. So that is going to be centimeters per minute, so that's going to be something over dt. Now be careful. Cubic centimeters. It is increasing at a rate of 800 cubic centimeters. Cubic centimeters always deals with volume. So that's going to be dV over dt. I'm inflating it, so it's increasing, so it's a positive 800. Now if I think about it, if I'm inflating a balloon with gas, my volume is going to be getting bigger. So it's the volume over time. Cubic centimeters per minute. That's what they give me. Let's look at what they want to know. As I read this, I want to know how fast is the radius of the balloon increasing. So I'm looking for dr over dt. How fast the radius is increasing. That's what I'm looking for. It's the first step. Second step, let's go ahead and come up with the formula that relates my given and unknown, which is volume and radius. So what would be a formula that relates volume and radius? Well, the volume of a sphere is 4/3 pi r cubed. So come up with the information they give you. I'm talking about a sphere. I give you the volume. I want to know the radius. So the volume formula of a sphere is volume equals 4/3 pi r cubed. Third step, let's go ahead and take the derivative. So that's going to be dv over dt equals, bring the exponent out front, 4/3 times 3 is 4, pi r squared, and that's going to be dr dt. So take the derivative. Make sure when you take the derivative of r, v, or whatever, you put dr, dv over dt. Fourth step is let's start plugging it in. Now as I look at this, I want to know how fast the radius of the balloon increases at the instant the radius is 30 and the radius is 60. So they tell me the radius, they tell me r, and I want to know what when the radius is 30 and when the radius is 60. So if I take my formula, dv over dt equals 4 pi r squared dr dt. Part 1, as I look at this, I want to know, look at what they give me. They give me dv dt is 800. I want to know dr dt, so they should give me enough information to just have dr dt left. Radius is, for the first part, 30, so I plug 30 in. And I want to know dr dt. So let's go ahead and solve this. A little more complicated than the one we just did. Very doable still. So this is going to be 800 equals 30 squared is 900 times 4 is 3600 pi. Divide by 3600. Reduce it, cancel out the zeros. That's going to give me 2/9 pi centimeters per minute. Make sure you label it, because that is dr dt. So that is how my radius is changing, which will be measured in centimeters, over how my time is changing, which would be measured in minutes. And then part B, I didn't leave much space, sorry. Part B, I want to know dr dt when the radius is 60. So plug in information. dv dt is 800 still, equals 4 pi 60 squared dr dt. So plug all that information. My radius is now 60. So that will give me 800 equals 14,400 dr dt divided by 14,400 pi. There's a pi there, sorry, I forgot it. And that will give me 1/18 pi centimeters per minute. Okay. So if you still have questions on that, there will be time tomorrow to ask. And the homework I give you will also have some examples on it as well. Okay, let's look at a couple more of these. Two more. Let's look at example 4. An airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles away, s equals 10, the radar detects that the distance is changing at a rate of 240 miles per hour. What is the speed of the plane? Okay, this one is more complicated. It's harder to kind of think about. We're not just talking about a shape, a sphere, or a circle. So let's see. An airplane is flying at an altitude of 5 miles and passes over an antenna. So let's look at step 1. Here's my antenna. A plane is flying, and altitude means the height. So this is going to be the altitude of 5. That's how high the plane is. Okay, here's my plane. When the plane is 10 miles away, so if I think about when I label my picture, something being 10 miles away, that's going to be the distance that is away from the antenna now. So my distance, this is going to be 10. Okay, S is 10, so this is S, or the distance. Now they tell me that is 10 specifically, and I'll deal with that in a second. When the plane is 10 miles away, the radar detects that the distance S is changing at a rate of 240 miles per hour. Like I said, 240 miles per hour is the speed, and that is always a rate, so that is always my derivative. A rate is always the derivative. Now as I look at labeling this picture, if I talk about the speed of the plane, that's going to be this way. Okay, now think about it. If I think about this, how fast the plane is going, that is how far the miles is traveled, how far it's gone over the time. So it's going to be a straight line. That is going to be the speed of the plane. Now if I go ahead and label my triangle, let's label this as X because that's horizontal. This is Y. We'll leave this as S. I like using X and Y. It kind of helps me keep track of things. Now they tell me that the distance S is changing at a rate of 240 miles per hour. What is the speed of the plane? I want to know, I misspoke earlier. I want to know the speed of the plane, so that is going to be the X part, because I want to know that speed. When I talk about the speed of the plane, I want to know how far has it traveled horizontally compared to the time. So that is what I want to know. I want to know the speed of the plane. Speed is always a rate, so I want to know, step one is to label what the unknown and what they give me. I want to know the speed of the plane. That's going to be dx dt. Horizontal, that's the speed. That's what I'm looking for. What other rate do they tell me? The radar detects that the distance S is changing at a rate, right there, ds over dt, the change in S per hour over time is 240 miles per hour. That's what I want to know. That's what they give me. Now let's go ahead, step 2, set up a formula that compares the unknown and the given. They give me ds dt. They also give me that my altitude is 5, so that's going to be the y part. So as I look at my picture and I look at my given, they give me a right triangle, and I'm talking about the sides, basically. Sides of a right triangle, we're thinking Pythagorean theorem. S squared equals x squared plus y squared. So a little harder to kind of come up with what formula we're going to be using, but it's going to be Pythagorean theorem because I'm dealing with that right triangle there. Okay, that's the second step. The third step, take the derivative. 2s ds dt equals 2x dx dt plus 2y dy dt. Okay, took the derivative. We do not plug stuff in until after we take the derivative. Now step 4, as I think about plugging stuff in, I want to know dx dt. So in the back of my mind, I should be able to plug in numbers for every variable part except for dx dt, because then I can solve for dx dt. So as I look at 4, we're going to have 2 times s. They tell me s is 10. ds dt, so I'm plugging stuff in. 2 times 10 ds dt. ds dt is 240 equals 2 times x. Now if I look at this, do they give me any information about what x is? I have my right triangle. Let's continue plugging in and see. So I don't know what x is. I'm going to leave a space there. dx dt is what I'm looking for, so that should be my only variable left. Plus 2 times y, which they tell me is 5. And then dy dt. Let's think about this. dy dt is going to be the derivative of y. Y is just 5. So what is the derivative of just 5? 5 is a constant. This is a little different. Y is an altitude. That is a constant in this case. So my derivative of that is going to be 0. So it's going to kind of get rid of that whole part there. So what I'm missing is I'm missing this x value. I can't just put an x because then I wouldn't be able to just solve for dx dt. Now as I look at this, I have a right triangle. If I think about my right triangle, I know y is 5. I know my hypotenuse or s is 10. So we can use, sorry, there's the picture. I know my height, my y value is 5. I know my hypotenuse is 10. I need to know x, or the other side of the triangle. You use Pythagorean theorem to help you find it. Now it's a little different. This is actual side lengths. So that's why we don't worry about dx/dt and all that stuff. We're not talking about rates. We're talking about like lengths, not speed necessarily, just lengths. How far away am I from the radar and antenna? So that's why we just use the Pythagorean theorem and not worry about the derivative stuff. So x squared plus y squared equals s squared in this case, my hypotenuse squared. Y is 5, so 25. S is 10, so 100. So x squared equals 75. Take the square root. This is a length, so we can't have a negative. So x is going to be a positive. Simplify this, 5 square root of 3. So that is how we had to find the missing side length, which is going to go here. I'll scrunch this in. It's going to go right there because that is my x value. So now, like I said, I have to be able to get a formula plugged in. There's 5 squared root of 3. It looks like crap, but that's okay. I want to be able to plug in enough information to just have what I want to know, which is my dx dt. So as I look at this, we're going to have 2 times 10 times 240, which is going to be, let me get a calculator. I should be able to do that in my head, but I can't. Two times 10 times 240, 4,800. Equals 10 square root of 3 dx dt, and that's all going to be 0. So divide by 10 square root of 3. So 480 divided by 10 square root of 3. We're talking about speed, so you don't really see square roots or anything. Plug it in your calculator. 277.13. Make sure you label miles per hour. That was dx over dt. X is a distance. So the change in the distance, which is miles. Change in the time, which we did in hours. Like I said, I know these can be complicated. Go through those 4 steps, and you'll be able to see those steps on some of the examples that I give you on the homework packet as well. Okay, let's look at example 5. Last one we're going to worry about today. I'll go over some more examples tomorrow if you still need help. A balloon raises at a rate of 4 meters per second from a point on the ground 50 meters from an observer. Find the rate of change of the angle of elevation of the balloon from the observer when the balloon is 50 meters above the ground. So let's think about it. A balloon raises at a rate of 4 meters per second. So if here's my balloon, here's my point, whatever, here's some person. So you can't see my picture. Here's some person who's sad because they lost their balloon. So as I think about it, a balloon raises at a rate of 4 meters per second from a point on the ground, 50 meters from an observer. Here's my point on the ground. That is 50 meters from an observer. Here's my balloon. We can kind of think about a triangle here. Now as I label this, let's do just like we did, right triangle. Let's label this axis horizontal. I always label as X. Vertical is Y. And then this will be my H or my hypotenuse or whatever. I don't have to worry about labeling that right now. So let's see what information they give me. A balloon raises at a rate. So right there, rate tells me derivative. So it raises, so it's going to be a positive because it's rising or increasing at a rate of 4 meters per second. So if I look at this, the height is y, so dy over dt, it's the derivative. So the meters per second, distance, which is y, over seconds, which is time. So dy over dt is 4, positive because it's rising. from a point in the ground 50 meters from the observer. Find the rate of change. Let me get my screen real quick. Find the rate of change. Now make sure we're talking about elevation, so we're going to be talking about an angle. So since we're talking about elevation, we're going to be talking about an angle. Find the rate of change of the angle of elevation. Remember, elevation is from the bottom up. Of the balloon from the observer when the balloon. So I want the angle of elevation of the balloon from the observer. So I'm talking about that angle, theta. Theta is usually used to represent angles in calculus. So find the rate of change of the angle of elevation, which is always the bottom horizontal up. So starting here up to the balloon from the observer when the balloon is 50 meters above the ground. So if I tell you the balloon is 50 meters above the ground, that is going to be my y value. Now, if I want the rate of change of the angle of elevation, rate is always derivative, so that is d theta over dt. That is what they're asking for. That is my unknown. This is all part one. Drawing a picture, labeling what you know, finding the rates, looking for the rate they give you, looking for the unknown rate. Step 2. We need to come up with the formula that relates dy over dt over d theta over dt. Now, let's think about this. It's a right triangle. I'm talking about an angle, and I'm talking about side length. So think about from pre-calculus, what formulas could I use if I'm dealing with right triangles, angles, and side lengths? Let's think trig, some sort of trig function. So as I think about this, we have to relate what is given to what I want to know. So I need somehow to relate theta and a y. So if I look at my right triangle, I'm going to relate the angle and the side opposite. Now I don't know anything about the hypotenuse, so I can't really use the hypotenuse anything. So if I think SOHCAHTOA, sine and cosine are both out because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, which those both have hypotenuse in them, and they tell me nothing about the hypotenuse. So I need to relate theta, my angle, with the side opposite and the adjacent. So that is going to be tangent. So tangent of theta equals y over x. So a little trickier to come up with that formula, but think about it. I have an angle that I know nothing about the hypotenuse. I only know about the side opposite, which is y. I give you the dy over dt, and then I tell you that x is 50. X is a constant. They tell you x is 50. Now, like I said, I've said this before, so you're probably going to be like, you told us not to plug in until after the derivative. However, x is just a constant. X is not changing. So in this case, we can go ahead and plug in 50 for x. Now let's go ahead and take the derivative. So derivative of tan theta is secant squared theta, d theta over dt. Now think about dividing as 50 as multiplying by 1 over 50. So that is going to be 1 over 50 dy dt. Okay, step 4. Let's go ahead and now plug in everything else. I plugged in x first because it was a constant. So step 4 is to plug in. I want to know d theta over dt, so I should be able to plug in everything besides d theta over dt. So as I go through, I have, let's see. Now, as I look at this, if you want to, you don't have to do this first. It's going to make it a little easier to work with. If you want to solve this for d theta dt first before you start plugging stuff in, it might be a little easier for you. You don't have to necessarily solve for d theta dt. So let's go ahead and solve for d theta dt first and then start plugging in. Either way, it's the same thing. So if I solve for d theta dt, I'm going to divide by secant squared theta. So if I think about this, if I'm dividing by secant squared, that's 1 over 50, dividing by secant squared, so really if I'm dividing it by 1 over cosine squared. Dividing by 1 over cosine squared is the same as multiplying by cosine squared. So that is the same as multiplying by cosine squared theta and then I have dy dt. So see what I did there, just to make it a little easier to work with. Before I start plugging stuff in, since I know I wanted to know d theta dt, I solved my derivative equation for d theta dt by dividing by secant squared theta. Remember, secant squared theta is the same as 1 over cosine squared theta. Dividing by 1 over cosine squared theta is the same as multiplying by cosine squared theta. So there's my formula. I want to know d theta dt, so let's plug everything else in. 1 over 50 cosine squared theta. It's a variable, so I need to make sure I get everything plugged in. I only can have d theta dt left. So I need to somehow figure out what my angle is, what theta is. Kind of like the example we did right above this. If I think about my right triangle, I want to know theta, I know x is 50, and if they tell you I want to know what is the rate of change, when the balloon is 50 meters above the ground. So if you read more specifically, they tell you I want to know the rate of change when it is 50 meters above the ground. So my y value is going to be 50. So now, if I want to know theta, tan theta equals 50 over 50, y over x, opposite over adjacent, or 1. So look at your unit circle, and I want to know what angle. If I take the tan of what angle, I need to get back a 1. Now, this has to be, there's two places you can do it, but if I think about my angle, it has to be in the first quadrant, because it's below 90 degrees. So what angle gives me, tan of what angle gives me 1, and that is pi over 4. So theta is pi over 4. So we had to do a little bit of work there to be able to find what theta was. And dy dt they give me is 4. So let's go through. D theta over dt equals 1 over 50. Remember that cosine squared, that squared can just go on the outside, so we can just look at what cosine pi over 4 is and then square it. So cosine pi over 4 is square root of 2 over 2 from the unit circle, and then pi over 4 times 4. Now be careful, because you want to be able to cross that out, but pi over 4 is an angle, so we can't cross it out, so it's still times 4. So be careful with that. I almost wanted to cross it out. So let's see, this will be 4 over 50, multiply the 4 on top. Square root of 2 over 2 squared is 2 over 4. 4 is canceled, so 2 over 50. So 1 over 25 radians per second. Make sure you label. Okay, so that should at least get you started on your homework. Your homework, if you get from the e-learning sub, is going to be the application of derivatives related rate problems. They go through some steps for the first ones. They give you 6 different examples to look at, and then at the end they have 12 practice problems. Some of these are tricky, so I would at least attempt all of these if you can before tomorrow, so that way you know which questions you have. Now you also have the answers on the bottom of it on the last page, so you can kind of check your answers as you go. So this should at least help you get started. Like I said, I don't expect you to be perfect at this by tomorrow, but at least you can kind of get started on the homework. Shoot me an email if you have lots of questions.